So what about gases in water? Can of soda is an example of a solution where you have a gas, carbon dioxide, dissolved in liquid water. Most liquids, including water, if they are exposed to air, they will contain dissolved gases. So tap water has dissolved gases in it. Lake water and ocean water have oxygen that dissolves into the water from the air, and that's what the fish need to breathe. Your blood has oxygen, nitrogen, carbon dioxide from the air dissolved in it. The solubility of gases behaves differently with temperature. Solids are more soluble at high temperatures. Gases are less soluble at high temperatures. And you're probably familiar with this from life experience with soda. A hot soda is going to go flat faster than a cold one, right? You leave a glass of soda out on the counter, you leave one in the refrigerator, the one that's at room temperature goes flat faster. You could try an experiment, you can do experiments at home, right? You got to keep people from drinking the soda in the fridge though. Yeah. When you're pouring a soda, maybe you've noticed sometimes they fizz up really bad and sometimes they don't. Well, if the soda's warm when you pour it, it's going to fizz badly. If it's cold, it's going to fizz less. There's also variations between different kinds of soda. Root beer makes a really big head of foam, and other things don't do that. So this is another thing you can try at home. Heat some ordinary tap water on the stove and just watch it. And what you'll see is before it gets to the boiling point, you'll see some little tiny bubbles forming. That's not the beginning of boiling. You've increased the temperature, and now the solubility of the gases from the air has decreased, and you see those dissolved gases leaving the liquid. As the temperature rises, eventually then you'll get to a boiling. The boiling, the water forms bubbles. Those bubbles are not air. They are water in the gas state. Before you get to the boiling point, it's dissolved gases that are leaving. The solubility of gases in water also depends on pressure. So let's think about, here we have a liquid and we have gas particles, and we'll pretend that this box is closed, right? So we have these gas particles zinging around. They move in straight lines till they bounce into something. Well, some of them are going to crash into the liquid and become dissolved. And they'll be in here, and then they'll get to the surface and they'll escape. And so we'll get one of those dynamic equilibriums like we saw with evaporation and condensation. So you have a pressure here from the gas molecules. If you put more gas molecules in here, if you put more pressure, then more of these are going to collide with the liquid and get trapped and dissolved in it. So if you increase the pressure of that individual gas, you will increase the solubility of that gas in the liquid. And that's what they're doing when they bottle soda or can it. There's a little headspace with pressurized carbon dioxide in there, and that's what keeps carbon dioxide dissolved in the soda. Once you release that pressure, the flattening begins. The bubbles come out, and they will keep coming out until it reaches the normal solubility at atmospheric pressure. And then you won't be able to detect any bubbles, because it's the bubbles coming out of solution that we perceive as fizzing. So of course this has to be quantified, and you've got to quantify everything, right? Oh yeah, I talked about that without the picture. So you open the can, you release the pressure, it makes that wonderful sound, psst, right? I don't have a problem with soda. I could quit anytime. I just don't want to. And then the bubbles start to come out.